Dear students, in this video we are going to start with the resistance welding. So far we have seen the fusion welding processes where heat is applied into the joint, but contrast to that, in resistance welding, the heat and pressure both are going to use without any use of the filler rod or the fluxes. That is the difference. The thing is that the heat is obtained, or the necessary heat is obtained to melt the joint by the heating effect of the electric resistance, and that is why the name of the welding is resistance welding. Here the contact resistance at the interface of the two plates is going to use for the heating. Now if you look at the principle of this process, so resistance welding is a low voltage and high current process where this very high current is passing through the joint for a very small amount of time. See, generally if I take the typical values, so the voltage is around 1 volt, the current is around, typical values I am saying 15,000 ampere, and the time which is up lesser than 0.2 seconds, and we are getting the heat which is generated at the interface of these joining plates, and at the same time the continuous pressure is going to apply till the material melts and fuses together to form a joint. So according to the Joule's law, if we look at the heat generated into this joint or welding, we can write heat generated, I will write Hg, which is equal to K times I square R tau. Well, definitely K is the constant for we are accounting for the heat losses, okay, but generally what we are writing, it is I square R times tau in joules, okay, where I is what? The current flowing into the circuit or joint. This is the current, and this is very high current. Please remember, very high currents I will tell you. R is what? The contact resistance, at the interface, and tau is time during which the current is passing through the circuit or joint. Okay, so this is the heat generated in the welding. So if you look at in this formula, so the resistance is very complex factor, and we have to get the idea about this resistance R. Okay, so if I take the simple example, say, of spot welding, so here are the plates in the lap joint, say, and this is the electrode, and of course we are having the power supply here. Now see, these are the electrodes, which can be the water cooled electrodes we are using in the spot welding, and here at the interface of this we are going to get this spot. Okay, and generally power source is always Of course, definitely we are going to use the alternating current, because this huge amount of current, if flowing like a DC, what will happen? These plates will simply melt. Okay, so of course the AC power supply with the relays, so that we will get the, in a given power cycle, only the current will flow for whatever the required cycles. Say if I talk about like this, say the power source is like 5 cycles for 50 hertz power supply. So in this 50 hertz frequency, only the current will pass through the circuit in 5 cycles, like that. Based on that, we can able to calculate the time for which the current is flowing through the circuit. But right now, what we are going to understand about the very complex factor in the resistance welding, R. So this resistance, if you look at the diagram, how many resistance are there in this? You can see here. So here is the resistance of the electrode. Say I will write it R1. Then we can have the contact resistance of the electrode and the plate. The contact resistance of the electrode and plate, I can say it is R2. Then I am having this resistance of these plates, that R3, and the resistance at the interface or the contact resistance between these two plates is, say, R4. Okay, so these are the resistances we are having, and where we are getting the joint, actually the joint is going to get, or the spot is going to get at the interface of the plate. Okay, not throughout the plate, isn't it? So for that, if we discuss about these 4 resistances, say I discuss about the electrode resistance. So here we are not going to melt the electrode. Okay, if the resistance of the electrode is very high, so definitely the electrode will get melt. So what we are requiring? We are requiring minimum value of R1. Okay, so R1 should be minimum, because it's a electrode resistance. Then if you talk about R2, R2 is the contact resistance between the electrode and the plate surface. So definitely it should also get a minimum, because we don't need any kind of joint on to surface, but at the interface. So R2 should be minimum again. Okay, say R1 should be minimum, again. Then R2 also should be minimum, as we don't want joint onto surface. Then R2 should be again minimum. If you talk about R3, so R3 is what? This is the resistance of the plates. If the resistance of the plate is maximum, what will happen? You will not get the spot, but you will get the throughout weld, or the plate get melted because of the higher resistance, isn't it? So R3 again should be minimum. Now let us talk about this R4. R4 definitely is the contact resistance at the interface of these plates, and yes, we want the spot there, we want to melt the material there, so we need the higher amount of heat should get generated because of this R4, then it's welcome. So that's why this R4 should be maximum, isn't it? Now if you go on searching the materials for, or what are the things we can have to minimize this R1, to minimize this R2, to minimize this R3. So see, R1, definitely here we are keeping this resistance as minimum, and this electrode is also going to apply the force, isn't it? So that is why we have to select such a electrode material that it is having very good conductivity. At the same time it should have some mechanical properties to withstand the pressure that we are going to apply during the process, isn't it? So definitely if we talk about this electrode, so steel is definitely tough, but it is not having that much electrical as well as the thermal conductivity. So very popularly we are using the electrode material in the resistance welding is the copper or the copper alloys, because it is having very good electrical as well as thermal conductivity. At the same time, we can give the strength to that copper by adding some alloying element so that it can easily withstand with the forces or the mechanical pressure when that we are going to apply during the process. Now if we talk about this R2 again should be minimum. So what we can do, we can keep a clean electrode tip surface. Also we can keep this surface, plate surface, very clean, so that there will not be any dust particles or there will not be any contaminating particles. So if you keep that clean, then R2 also get minimum. Now if we talk about this R3, so see here, resistance welding is having the limitation that if you are going to join the materials which are having the maximum material resistance, then there is a limitation. You cannot go for the resistance welding for such a kind of material. So you have to take such a material that their self resistance is minimum. We are choosing the material such that their resistance is minimum, and we can use those material into the spot welding or resistance welding. Now again if you talk about the R4, so how to increase the R4, because we are interested to have the increased R4, maximum R4. So again please remember that R4 can be increased by having some rubbing of the surfaces, but at the same time if there is any kind of dust or contamination particles are there, these get into the joint, into the weld, and that is not allowed. So only we can have the proper cleaning as well as you are having some rubbing of the plates, okay, at the interface, so that we can increase the R4. So in that way, if I talk or if I want to write about the average resistance, this R in totality into this welding, that is 2R1 because there are two electrodes, plus 2R2 because there are two contacts at the electrode and plate, and again there are two plates, that is 2 times R3, but there is only one contact resistance at the interface of the plate, that is one and only R4. So we can have this R as 2 times R1 plus R2 plus R3 plus R4. And if you look at this resistance welding, so the average resistance we can have up to the 100 ohms, okay, so average value. Now let us talk about the current. We have talked about in the formula. What was the formula? This heat generated Q was equal to I square R tau. So we talk about the resistance. Now if I talk about the current, so see here, now see if we talk about the current conditions into this resistance welding, so the current is very high. If you take the range of the current is from 9,000 to 12,000 ampere, but some cases it can go up to 40 to 50,000 also, okay. So here if I take the steel of say steel plates of 1.5 mm thick, 1.5 mm thickness, then to join this place by the resistance welding we have to use the current of 10,000 amperes. 10,000 ampere. Okay, this is the standard one for the steel. So the very huge amperage is required. That's why the heating is obtained there, resistance heating, isn't it? So this is about the current. Now if I talk about the time, so tau is what? The time during which the current is flowing through the circuit. So definitely this huge amount of current is flowing through the circuit for a very shorter period of time. It is generally less than 0.2 seconds and up to the milliseconds also. So for that reason, what we are supplying here, the power, the AC power supply with the relays, AC power supply with the relays. So here, for example, say if I am having the 5 cycles of 50 hertz power supply, that means I can get the time as how much? This 5 cycle divided by given power supply, that is frequency. This is the frequency. So it is generally, say it is 0.1 second. So for 0.1 second the current is going to flow through the circuit. Okay, so these are the 3 things we have discussed now. Now see here, that is heat generated, heat generated, or here heat required to get this joint. If I say this proportional to the I square and also proportional to the, say it is again proportional to the, because see, as we know, the welding process thickness goes on increasing, amperage is increasing in this proportion. So I can write here this I square is proportional to the, okay. Now I have taught you that for steel of 1.5 mm thickness, it required the current of say 10,000 ampere. Okay, from this relation what we can get, if say the thickness, I want the say thickness of 3 millimeter to get joined by this resistance welding of same material, then what will be the current? So we can calculate, say this is the T1, this is I1, this is T2 and this is I2. So very easily we can calculate how, that is say I2 divided by I1 will be equal to say under root of, directly proportional, so T2 divided by T1. So how can I write I2 divided by I1, or I2 is equal to, I1 was how much? 10,000 into root of thickness T2 3 millimeter, initial thickness was 1.5 meter. If we calculate, we will get the current for this thickness. So how much it is? 3 divided by 1.5, root of answer into 10,000. So we will require near about say 14,000 amperage for this process. Okay, again this heat generated is also proportional to what? Is also proportional to the melting point. Okay, and in that proportion we are also getting the I square is proportional to the melting point. Yes, say this for steel, if I take the melting point as a 1400 degrees centigrade, okay, and say now I am using some another material, say if I take the aluminium, say the melting point is around 660 degrees centigrade. So again we can have the relations like this, this I2 by I1 is equal to under root of MP2 by MP1. Okay, like that we can, because see this resistance welding technique is suitable for joining of the similar composition material with the different thicknesses, and also the different composition material with the different thicknesses or equal thicknesses. So we can compare, comparatively you can calculate the required current conditions, isn't it? So if you are having both the data, say melting point temperatures, then thicknesses, then and current also, we can get the relation like I2 by I1 is equal to root of T2 divided by T1 into MP2 by melting, MP is what? Melting point of 2 by melting point of Like that we can get the or generate the relationships. Okay, so it's very simple. So students, if you talk about the electrodes, the electrodes, so the important characteristics of the electrode is what? It should have the good electrical conductivity as well as the thermal conductivity. At the same time, it should be strong enough to withstand with the mechanical pressure applied on it, isn't it? So we have seen, or I said last time, that the steel is having quite good strength, but it is not having that much conductivity. So that is why the most commonly used the electrode material in this resistance welding we are using as the copper, having a very good conductivity, but it is not having that much strength required to withstand it with these mechanical pressures. So what we are doing, we are using the alloy of the copper. So in the alloying, we are adding the cadmium into the copper. When we add the cadmium into the copper, say from 0.5 to 1%, okay, so it is having very good electrical conductivity, but also it is having good electrical conductivity, but moderate strength. That's why this copper with this 0.5 to 1% of cadmium is used for the joining of the non-ferrous materials like the aluminum and magnesium alloys. Please remember. Next, if we add the chromium into the copper, the chromium from 0.5 to 0.8% of this chromium, then we are getting this electrical conductivity slightly less than this above condition, but you are getting a very good strength for the electrode. So slightly less the electrical conductivity, but better strength, and that is why this electrode can be used for the joining the plates of material, say low alloy steels, or for the mild steels. Okay, but again, if we are going for addition of say beryllium and cobalt into the copper, so no doubt the electricity is decreasing in more amount, but at the same time you are having very high strength for the electrodes. So that is the reason why they are used in the welding of say stainless steel plates or these steel plates with the tungsten plates. So we can use that combination. So very high strength for the electrode. So these are actually the alloying elements which are added into the copper to enhance the strength for the copper electrode, so that it can be very easily used in the resistance welding. Now if you look at the shape of the tip of the electrode, we are having various shapes which can be used at the tip of the electrode. We are having the flat electrodes. This is a flat. We are having the dome. We are having dome shape. Okay, this is a dome. Then also we are having some eccentric shape. This is the eccentric. So we are talking about the tips which are available. We are having the spherical. Okay. Then we are having, this is the spherical. Then we can also have the truncated. This is the truncated. So these are the various shapes of the tip of the electrode which are available. Okay, flat, dome, eccentric, spherical or truncated. These are the various shapes of the tip of the electrodes. Now, suppose if I going to count the advantages and disadvantages of this resistance welding. So first of all, I will write some advantages of the electrode, of the resistance welding. So here there is very less skill is required by the operator to perform this resistance welding, as these machines which are used in the resistance welding are semi-automatic or automatic. That is why a lesser skill is also okay with the operator because of these semi-automatics and automatic machines. So less skill, first of all, what? The less skill is required to do this operation. Second, if I talk about, see here the production rates are very high. The production rates are very high. That's why this resistance welding is applicable or suitable for the mass production. This is suitable for the mass production. Okay. Now the third thing is that as here the heat zone is confined, it is limited to only that spot, isn't it? So the heat zone is confined. That's why there is less distortion you can see in this resistance welded parts. Okay. Now if you talk about, see the consumables which are used in this process. The consumables used in this process are what? Only the electricity. What are the consumables? It is only electricity. That is electric current we are using in huge amount, and the wear of the electrode. Wear of the electrode. That's why as the less consumables, it is quite economical process. It is economical. Okay. So this is the economical process. So these are certain advantages of the resistance welding is there. Now if we look at the limitations or the disadvantages, and of course one of the very important advantage, I already talk about this in the early discussion of resistance welding, that the similar or dissimilar materials, very important. I can write here the similar or dissimilar materials with same or different thicknesses can be joined. Okay, so this is very important, which can be included into the advantage. Now if we talk about the disadvantages, what? So only thing is that, see, these resistance welding equipments or the machineries are very costly. Okay, because see, there are the electrode setups, there are water cooled electrodes we are using, then we are having the heavy transformers, large electric conductors, So again, for the mechanical pressure that we are going to apply onto the plates, so we need the piston cylinder and all these arrangement. So overall the cost of this equipment is very high. So the thing is that it is very expensive. The main disadvantage of the process is what? It is very expensive. It is very expensive. And the second important limitation I can say, so in the spot welding, most of the time the joining is preferred in only the lap position. Okay, so most of the times what we are having only lap position. So it is not necessary that each and every application of the say automobile industries, any industries or aerospace industries only require this lap joint. Okay, so that is one of the again limitation of this, that is we are maximum times we are do welding in the lap position. That is a limitation for the resistance welding. Understood? So these are certain advantages and disadvantages for the resistance welding. If you look at the cycle for this resistance welding, okay, cycle means these are the events of these are the events which are happening into the resistance welding. Usually they are giving on the pressure or force versus time, force or pressure versus the time. Okay, so the cycle of this welding like that it will continue. So these are the parts we can have here, or these are the various times we are having here. This is the squeeze time, this is the weld time, this is the hold time, and this is from here say this is the off time. So see, in this resistance welding cycle, so this time get divided into C. So these are the time events we have plot against the forces. Okay, so there are the 4 times we are having in the cycle of resistance welding. That is squeeze time, I can put the title as the cycle of resistance welding. So these are nothing but the continuous events which are took place in the resistance welding. So what is squeeze time? So this is the time actually where in this time the electrodes are get aligned to each other, the workpieces are put together into the required position. The time is this squeeze time, or rather we can also say that it is a time during which whatever the air which is present between the electrodes and the workpiece surface, it is getting squeezed out or driven out. That is known as a squeeze time. So it is simply you can write the time during which here the electrodes get aligned or the plates are get in position, or squeeze time, it is time during which whatever the air which is present between the joint is going to happen, air is squeezed out, squeezed or driven out. Okay, so this is the squeeze time. Now what is the weld time? So this is the first squeeze time. Then weld time is what? Now this is the time during which the electric current is going to pass through the joint, isn't it, or from the circuit. So here the electric current is passing through the joint. Okay, so this is the weld time. Now what is the hold time? So in the hold time, see, now the current is not flowing through the circuit. Now current has stopped. Now we are only applying the pressure. We are only applying the pressure by the electrode onto the plates, so that which molten material is fused there until it gets solidified or the spot get produced. We are applying this pressure onto that plates. So this is the hold time. So current is off now. So here current is off, but pressure is continued. Pressure is continued till the melt get solidified or cool. Okay, so the joint can happen there. It is a hold time. And what is off time? So off time is what? Now the after completion of the joint or completion of the spot, the electrode now should ready for the next spot. Okay, so it is nothing but the time for preparation of the electrode to have the next spot. That time is known as the off time. Okay, so that time is known as off time. That is what? Now the electrode getting prepared for the next spot, so that the time for that it is a off time. So electrode preparation time for the next spot. Okay, that is these two electrodes. This after completion of cycle, for this off time, these two electrodes will move apart. Then the next position will be settled for the next spot, and then again the new cycle of this resistance welding will start for the new spot. Okay, so this is how we can have the cycle for the resistance welding. So in the resistance spot welding, the only the thing is that the electricity is having the shunting property. Shunting means whenever there is a continuous media is there, the electric or current is trying to bypass. Okay, so that is known as the shunting of electricity. So here in this resistance welding, what we are having, resistance spot welding we are talking about. So say once the spot is made here, and initially the electrode at this position, okay, and now the spots is moving, we are moving for the next spot. Okay, and definitely we have applied the huge amount of current. This is power supply. Now what is mean by shunting of electricity? That is, now to have the next spot, the electrode will go apart, then the position will be settled out for the next spot. So here, and whatever the current is required for getting that spot, say we are talking about 10,000 ampere current we are requiring. Okay, so what happened, because of this continuous medium the electrode is having in contact with these plates, and because of this continuous medium there is a bypassing of the current from this continuous medium. Okay, so say out of this 10,000 which is required for the again next spot, say there is a shunting of 3,000 ampere current. Okay, so of course at this next spot, so here definitely the current of 3000 ampere is moving or passing through these plates because of this tendency of electricity to bypass the current, that is shunting. So to avoid this shunting of the electricity, see, because we required 10,000 ampere here only, but 3000 is currently it's bypassing because of this shunting property. So for that reason, in the resistance welding and resistance spot welding rather, the spacing between the between the two spots, the spacing between the two spots or distance between the two spots is maintained around 48 times thickness of the plate, so that the shunting can be eliminated. So if this distance between the two spots, if we put this 48 times thickness of this plate, see the thickness of plate T, then we can able to eliminate this shunting and required current can be obtained without any loss. Okay, so this is a thing in resistance spot welding. Okay, so in next video we will see the nugget geometry for this spot weld, then seam welding, projection welding and percussion welding. Thank you.